So unless you're willing to drive to Fayetteville to go to the conference, and then if you even did, I wouldn't talk about dynamics. So we'll cancel next class, and then we'll reconvene on Friday, or redo it on Friday. So I don't know what I mean by redo. So I'll be out of town. So let me just do this. Instead of going to the book, I'm going to use this as a backdrop and just make up a problem and do it as soon as I get this thing to come up. And
we're still going over chapter 16?
Yeah. 16 is actually going to go for a while. So I'll give you a layout of it in a second. It says, oh, there we go. So 16 has actually 4 components, of which one of them isn't, I think, critical, but it is there. So let me kind of lay out 16. So we've already done part of it where we started relating the symbol for velocity and the symbol for that. And we had S was kind of like that. And we had an acceleration which turned into this. And so then this is for rotating. And then for, I'll just say linear. And then we had an equation S. This was a while back. We had this for constant. Okay, so for constant, we had this. Whatever the constant acceleration is, times t squared. But then you look over here and you see the same or similar thing. And so we had t, we had this, so if you just replace it, and then 2. So we already did this part where we were looking at these terms look exactly like those terms. And so then you end up with omega is equal to d theta dt, or sometimes called theta dot. And then we end up with alpha, or the same thing, 2 of the thetas, or I guess you could put down theta double dot, or you could put down omega dot. So he sent us through a series of problems that were related to this. Then we went on and we said, okay, now we have, this is for rotating stuff. And then the next thing we did is, let's say we had some sort of rigid link. So at this point, it's kind of implied that it's rigid, but it's not really specifically said that it's rigid, I think, yet. And then at this point, we reach the point where we're at some location A and some location B, and maybe we're sitting at A. Here, we'll do it like that. There's A. So there's A, and you look at B, and it appears to be rotating around you. And so then we end up with, say, velocity of B. You could do it either particular way. Velocity of B relative to A plus velocity of A. Then we focused for a minute on this, and we said, hey, this particular part looks like all this stuff that he had back here, in that it's rotating, and it appears to be rotating. If you're sitting on A, B appears to be rotating about you. And then technically, I don't think he specifically says this, but you know, this is your coordinate system where this is positive these terms. And the reason those are positive is because, you know, you cross it and you have your finger coming out, and that's a right-hand coordinate system. And the next thing he does is he says omega. Sometimes he doesn't have a subscript, but it's better to have one because it designates that this omega is associated with that rigid link. And then this, and we, or he, actually took us through this part earlier, like that. And so he said this is pure rotation. This is the movement of A. You know, A might look like this. In other words, the path of A might look like this. B might be rotating. If it's not rotating, it's just going to be doing like this. If it's rotating, it may be looking like this, you know. So, in fact, this motion is only because of rotation. If there was no rotation, that would be gone, and velocity of B would be the same as velocity of A, meaning it would just be floating along without rotating. So then we did problems like that. Then the next thing we did is instant centers, which I'm going to pick up at that for a second. And then the last thing we're going to do is when we do the accelerations of these things. And that probably I'll finish up on Friday, and then we'll just work a bunch of problems. So in essence, there's four main groups here. There's this group that's early part of it, and it's kind of a mirror image of what we saw before. There's this, it's getting this concept laid down. There's two ways to work these, and I'll show you, I'll pick up a problem. Excuse me, work them both ways. And then unfortunately acceleration is all by itself, but it's a hybrid or carries on from here. And actually that acceleration was talked about back here, but these are the four groups. So let's just make up a problem that will cover this group and this group. I guess that's 2 and this is 3. And we'll work the problem both ways. And does that kind of lay out the thing? That I go a little slower here in this chapter because the problems are deeper, and these problems, unlike the others, are more indicative of what you would actually do in a job site if you worked for a company that did this. If you didn't, you would never use it. So.
You want to take a picture of that?
Sure. I mean, it's being streamed too, so if you want to, yeah, you can do that. So that's the layout of the 16. Yeah, and the thing is, like I said, when we go back to the other, okay, so we're gonna go. We did 12, then 16, then we're gonna go back to 13, 14, 15. You'll find those have some value too, but those are more analysis things. This can put you on the forefront of designing mechanisms in some sort of assembly line, but it's not quite there yet. There's another course you can take called Mechanisms, which I think I don't know if it was offered last year or the year before. Anyway, it will actually show you some methods of designing mechanisms to do things that you want to have done. So let's do a problem that's related from here to here, or related to both. And let's just make up one. I'm going to make it as complex as I can to have all of the funniness associated with it. So I'm going to do this. It's going to be a crank. So my rigid members are just going to be lines, if you're okay with that. I'll make it kind of go to here. I'll make it kind of go to this. Okay, and let's see, what else can I do? I can make it kind of go, I know. I'm just making it weird. I'm just trying to make it as weird as I can. And it pushes this thing. And instead, I just want to make it weird, so I don't want it to go too predictable. I want it to go up like this. This is really strange. Okay, and I'll say this is that looks like about a 3, that looks like about a 4, and if that's a 3 and a 4, then that's a 5. So I got to label things A, B, and C, and D, and I guess in suit I'll call that E. Now what I'm going to do, okay, there are two ways this could be presented. It could be presented as though there is a distance from A to B in an angle, or I can just have the coordinates. Either way is okay. And as a matter of fact, just to mix things up, I'm going to do this both ways. Here's what I'm going to do. This is 45 degrees, and I'll say this is 6 inches long, or okay, it doesn't really matter what the unit, so I'm going to say it's 6 feet long. So I don't know why you would want to have a 6 foot length doing this. It really doesn't matter. It can be 6 feet, 0.1 feet, doesn't matter. I'm just going to use round numbers. And you know what? I'll do it this way. Here's what I'll do. I'm going to make my life very simple. I'll say instead of 6, I'll say 3 times square root of 2. That's the length from A to B is equal to 3 times square root of 2. You'll see why that's the case in a minute. Very odd, doesn't really matter. I don't know. So now I'm going to intermix things. I'm going to say, well, the distance, and you could draw this out in a CAD program if you wanted to. And actually there is a benefit to doing that. Okay, so if that's that, okay, so this distance I'm going to say from A to D is 8. That sounds like a good number. If that looks like about 3, 2 3s, maybe it looks like about more like a 6. Okay, so I'm going to try to make it as much to scale as possible. I'm sorry, that's 3. 3. So I think I was right before. I think it's about 8. If that is a 3, this looks like about a 2. That looks like a 4. If that's a 2, that's a much larger than that. Okay, I'm going to make that a 5. Okay, this, if that is that distance, that's bigger than 5, smaller than 8, how about 6? Here we go. And that's all I need, except one more, actually, and that is, how do I do this? I can go over to about right here, and I'll do it up from D, that distance. Okay, that looks bigger than that, smaller than that, so I'm going to say it's a 3. So if you wanted to, you could put this in a CAD and draw it up, and you'd find positions of everything. And what I'm going to do, I guess I should have implied that. This is a piston going up and down this little channel here. So let's now come up with stuff. I'm going to say the thing is rotating this little, there's an engine back here making this thing rotate with 10 radians per second. Now, first thing I'm going to do, here, let's take this. Length from A to B is equal to 3 square root of 2. I'm going to use this space. We'll see why in a minute. I need this space. Okay, instant center. Let's start there because that's a geometric kind of thing. So remember, on an instant center, you had a rigid body, and you knew the direction of the motion of two different things. All you do is you come to one of them and you say, I know if it's rotating, I draw a line that's perpendicular. So what you do is you find any point you know that you know this velocity. I drew a vector that way, but it could be going the other way. It doesn't matter. The perpendicular is this. Yeah. And now I got that little B in the way. So let me move the B over to the side. So here's your B. You stare close at it and you draw a line that is 90 degrees. And I'm sorry, these don't look like they're 90 degrees, but this appears to be the instant center. So the key is 2 points that you know the direction. You don't even need to know the magnitude to draw and find the instant center. You just need to know the direction that these 2 points are going. And then you draw perpendicular, and suddenly it looks like this thing is rotating about that. Okay, so let's look at the number of links. We got 1, 2, 3, and 4. This one and this one, really simple. Super, super simple. The instant center is, right here for that link. But the instant center is different from every single link. So technically, okay, I know the velocity of this thing here. Let me move my letters around so I can. Okay, so I know this thing is spinning, so I know the velocity is like that. So I know this velocity is going like that. And use as much color coding as possible. Well, that's not part of the member, so let's do it like that. So there's that. Now, this member, okay, here. It's hard to think about where things are going to go before you draw them. So this one has to go like that because it's pinned to go around this point. So this thing is spinning around this one. This one's around and around here. The instant center here, there's an instant center right here for that link. This link, however, if you want to find the instant center of the BC, you take the velocity. It's almost as if you can, in your brain, erase this and erase this. And now you have a member which is sitting out here, in which you have a velocity going like this, and you have another velocity going like that. This is B, this is C. You forgot all about this, you forgot about that, you're only looking at that link, and suddenly you can find the instant center here. So I'm going to do my best to do that, and unfortunately it goes way up there. So what I'm going to do, you know what I might do? I might, shoot, I should have brought my other laptop because I have a CAD program on it. I can show you how to do these problems like super quick in a CAD program. And all you're doing is you're taking lines and you're finding distances and using dimensions. So maybe what I'll do is I'll do the drawing here. I'll do the velocities the traditional way. And then on Friday, I'll bring in my laptop and my cord, if I can find it, and connect to that thing and project my laptop on the wall. And I'll sit here and I'll show you how you can do these with CAD. Because a lot of people in the industry, that's what they do. They'll do them with the CAD thing. The other thing you can do with CAD is you can move the members around, but we don't want to go that far quite yet. So in fact, if I were able to find the distance from here to wherever that point is, and the distance from here to wherever that point is, and maybe I'll do that in a minute, then I can use that, and this member appears to be, here's omega CB or BC. These can be interchanged because this is just designating the linkage between the two ends of the rigid link. So if I want to know this, I would say D instant center to B, and the distance from instant center to C, and I can figure out all of this information, and I'll attempt to do that in a second. Now here's another thing, okay. It just so happens, I have another color, and that's great, because let's move to this linkage. Okay, I know this velocity. If this is pulling this way, it's going to be heading down that way. Guess what? I take this, and I find a location right here that's actually the instant center of CE. Why? Because that velocity sat on this link, but that velocity also sat on that link. This one's perpendicular. I mean, it's forced to go up and down this whole thing. So it's forced to do this. So its perpendicular looks like that. And what you find out is you can visualize all those pretty rapidly. If you had a CAD program, what you do is there's a way you can draw parallel lines, and then there's a way where if two lines intersect, you can set a point on the intersection point. And that would be the instant center here, and that'd be the instant center here. So in order to clean this up, and actually, since I have such a nice picture, if you don't mind, I'll take a picture of it myself, so I can go ahead and put this in the CAD and bring it in on Friday. And now we'll work it. Oh, there's a reflection right on that, isn't there? Let me turn on the light and see if that helps the reflection. Actually, no. What I can do is I can cut off the projector real quick. Let's do that, and then I'll turn on the lights. Because I don't really need the projector if I'm doing this way. Oh, this is a mystery. Okay, wait. This mystery of how you get this thing going. Okay, so I'm going to take a picture of this. It still has some funny reflections, but I can get the measurements and put it in a CAD program and bring it in on Friday. If I forget, I'll make it the CAD program on Friday. So let's do it the traditional way, since I'm going to bring that in. And what I'm going to do on Friday is I'm going to bring in, find this distance, and this distance, and maybe I'll try to do a little bit of that today, but I'm going to do it the traditional way first. In the traditional way, you can run down links. Okay, here's what I mean. You can go from velocity of B equals to velocity of B relative to A plus the velocity of A. The key is B and A must be on the same length. B on same rigid link. So the mindset that you're taking on this is the same as instant center. You're focusing on a link, you're working between A and B. You focus on this link, you're working between B and C. And so on and so forth. So what I mean is this. I'll have another equation. Velocity of C equals velocity of C relative to B, because they're on the same rigid link, plus velocity of B. Then I've got a velocity of C that is also stuck on this link. Velocity of C relative to D plus velocity of D. And then I got the last link, which is this one. Velocity of E is equal to, or I could write it the other way. It doesn't really matter. Velocity of E relative to C plus the velocity of C. And what you find in here is each one of these is the link. So these are the links. I either have a AB, like the first one. I have a CB, which is like the second one. A CD, and I have a CE. Oops. So I have 4 links. You can see there are 4 equations. There are 4 links right here. 4 links for 4 equations. So let me just go ahead and start with one, and I'll start with the A. And so what I'm doing is I'm starting with this one. So I'm going to do this one first, then I think I'm going to do this one second, and then I'm going to do this one third, and this one fourth. No particular reason except that I know on one I know I want to do this one first, because it wraps up really quick. So velocity of B is equal to, now here's the beauty of all of these, is all of these end up with like a velocity of B relative to A, for example, is omega AB, the link, cross R B to A. So each one of these, what you notice is this and this. You notice this and this. And you notice this is the length identified with the AB. So this is the rotation of that length, which we've given as 10, crossed as a vector, crossed with the vector that goes from, starts at A and ends up at B. So if I draw a vector that starts at A, ends up at B, what do I get? That vector R, okay, so location B relative to A is equal to, now, I'm going to write this out here. I'll write it down here because I don't know if it can show on the camera, does it? Oh, I take that back, it can. You can see it on the camera. So here, I'll do it right here. Equals 2. Now see, here we go. 3 square root of 2 cosine of 45i plus 3 square root of 2 sine of 45j. Why? Because I had an angle and I had a length. But it turns out the cosine of 45 is equal to the sine of 45, which is the same thing as 1 over square root of 2. So I rigged this problem so that RB relative to A was just going to be equal to 3i plus 3j. And that's why. I was doing it because you can list them as lengths and angles, or we can find the actual physical coordinates of each of these points, because we have distances. This is what you would see in a CAD model. You'd see the x, y of all these points. You would know how to draw them that way. So, what do we have? We look over here. We have I, J, K. What am I writing here? I'm writing actually that. I know, okay, I had my coordinate system at one point. I think I erased it. So let me put it here in red. And basically, you should, I'm not telling you how to think, but I guess that's why you're here. I always look at it like that. X that way, Y up, and this is a positive, you know, the I crossed with the J gives you a K direction. So that gives you positive coordinate. Turns out that's 10 going in that direction, so that should just be 10. And then I get 3 and 3 and 0 plus velocity of A. So lo and behold, that's 0 because it's pinned right there. And so what you end up with is you end up with a version or a portion from A. You don't end up with anything from K. You get this, so you eliminate this and this one. You take the 0, the 3, the 10, the 0. Then, believe it or not, just because the way this thing is constructed, you take the 0, the 3, and then if you want to add it, have at it, but basically you get 0, 0, 3, 3. This term always ends up being 0. So you get 0 times 0 is nothing, minus 30i, minus gives you back a plus 30j, so my velocity of B is just going to be that. Okay, so that actually is a minus sign. So you know, with minus 30, well, does that make sense? Okay, let me isolate that and stare only at that link. So I have a link here that's sitting here that's 3 long and is spinning at 10. So the magnitude of this velocity is equal to 3, that distance times 10. It was 10, right? Wasn't it? Yeah. Well, that distance is 3 times square root of 2. So that's going to, what's that other line for? Okay, wait a minute. So it's 3 times square root of 2. It becomes that number, whatever that number is, 30 times square root of 2. So it turns out if you look at this, that squared plus that squared does become 30 times square root of 2. The other key is I get a negative this direction, and I get a positive that direction. Negative, and then positive. The other key is, and this is my check, is I'll take this number, multiply it times that number, add it to this number times that number. If I take that times that plus that times that, then what I'm saying is that this is a dot product with this, with that vector R, means they're perpendicular, means that the dot product is 0. What it means, essentially, when I do that, is that whatever vector I get here, it actually is perpendicular to the vector here. This is the vector R, B to A. You know that this vector has to be perpendicular to that, which means I take this, dot it with that, I get 0. I have to get 0. So by definition, I have a check middle way through. I can take this. I can also take it and multiply it times that, but 0 times that plus 0 times that plus 10 times no k component. It's easy. There's no real check there. This one is a mathematical check that you did this, these two multiplications right here correctly. Okay, so now that you've got that, what do you have? You have that, of course. And what that tells you is I have this one, which is there. Now, I can run down this length. And so, it depends on the way you want to do it. I think I'll run down this length and then run down this one. Because, why? Because this thing and this thing are the same. And so, I could actually do these two across with these two and work this out. In other words, I could combine these. Hang on. It depends on if you like doing that. Some people might not. In other words, they may take these two equations and say, hey, look. And then I get here. That's supposed to be D. So I took this one and this one, and these are two the same, so then I take B and then this. So the justification for doing it one way for the other. I don't really know that there's a justification for doing it one way or the other. I just have to be regimented in making sure I do these correct. So what I'm saying is this and if I want to focus in, I can focus in on that one because this is where most of the work takes place. Mega DC, which is these are two different links. So I'm hesitant to do it this way because this is operating on one link and the other link, and they're combined. But I guess I'll renege a little bit and just go ahead and write it this way. And we'll just go with it. So really, most of the work occurs right here. If you happen to notice, this one's pinned as well as that one. So these are both pinned, which means that one doesn't, and I guess I could have designated that right off, is that pinned is equal to 0, and is equal to 0 because it's pinned as well, which makes it a lot less complex. It's just you're doing two different links in the same equation. So we'll go ahead and do this, but if you feel like you need to do it separate, do it separate. It's okay. But since that C is and technically C sits right here, but I don't want to go too far into this. I think I want to do this one by itself. I think C sits on 3 rigid links. And so that being the case, you just gotta figure out which one you're gonna do. Some people might want to run down this one and then run down that one and then combine. So let's go ahead and do these right here. Guess since I already used that, and since I might actually need this space, I'll do it this way. I'll kind of spread out to the left here. Here's a funny thing. I don't know what the omega is. I know it really looks like this. I know if I do this problem this way, I should get the same number. I don't know what that is. I'm going to do that one on Friday. But this one, I know that I don't know. And so I'm going to use my coordinate system and assume it to be this way, and I'm just going to put my value in there. I don't know what the value is. So this is a scalar, this was the vector. The vector has these components, or C, B. Now that's a vector that starts at B, ends up coming down here to C. Now, unfortunately, I have made my life a little bit complicated, and here's how I've made it complicated. Okay, so now this is on the video, so I don't even need that. I'll use this space to work out, but I'm going to keep this here for right now. I'm going to work out the vector that points to C and originates to B. Now I know it goes to the right, but I know the distance from here to here, actually, I may actually have not complicated my life. This distance is 3. So in other words, technically this is 3. And technically, this is 3. So I know from here down to here is 3. I know from here to here is 3. But I know from here to here is 8. Take away 3, and that means this vector, and I can draw it and then I'll erase it, is 5. And the vector down here to C would be 3. And I didn't designate how far below this it was, did I? I didn't put a dimension from here to here. Let's make one up. Okay, so if that looks like 3, to me that looks like 3. How about that? So my early picture doesn't have enough information for me to do the CAD drawing. I need that 3. So if you don't mind, let's take another picture. Okay. So I omitted that 3. So I go down 3, go down another 3. So first thing, I go to the right 5, and I go down 6. So to draw this in a CAD drawing, you would need to come, you need to set your coordinate. The easiest thing for me would be set my coordinate here, and then on up here to Y, and then work off it yet. But I'm going to have that to draw the CAD drawing. So it's a little busy, but it's okay. So there's your 5 from B to C. Then there's your 6 runs down from B to C. So I'm going to have to do this again for this one. So 5 minus 6. And now, I could enter this B, but I'm just going to keep it there for a minute to really focus on each of these terms. Okay, nothing. Omega DC, okay? I don't know it yet. I don't know how. I know this thing is probably rotating like that, but I don't know its value. I didn't even know the length right here to here yet, but that's okay. So on this one, That's what I'm looking for. Or drawing 2C originating from D. So I draw a vector from here to there. Well, if I go over to the right 2 and up, looks like 5. Okay, so this vector goes over to the right and up. So, and that's what this vector is. So it's 2, 5. And again, there's nothing here, so there's nothing to write over here. Now, what I'm going to do is do this, work it out, check it, and think about this, and then do this one, thinking about link DC. So here, my mindset on this one's going to be BC, this link right here. So as I work this out, I take the cofactor expansion, and then take that off and that off, minus 6, 0, minus J. Take that and that off, 0, 5, negative BC, nothing. And I'm just going to put this down, and I'm going to focus on this, just this part for the moment. That times that, minus that times that, gives me 6 omega BC. That times that, a minus this, but there's a minus there. So it becomes plus 5 omega BC, J plus BB. Now I isolate myself to stare at just this, not focusing on that at all. And I dot it with that row. I could dot it with either row. Both rows are supposed to give me 0, but like I said, 0 times that, 0 times that, that times a 0 component, which is not written. But if I multiply 6 omega BC times 5, and 5 omega BC times minus 6, add them together, indeed I get 0. So this vector is perpendicular to that vector. Now, let's draw it. Okay, or try our best to draw it. Okay, now let's think about what this term is. It is velocity. It's the one that's sitting right here. C relative to B. So I'm going to draw this. Here's your link. Here's C. Here's B. The velocity of C is if we are sitting on B. We don't know its rotation, but we're assuming it to be positive. This is positive, so it means it's rotating like this. So again, the velocity, okay, to focus in on this, only this, you're assuming that the person who's sitting on B is in fact fixed. They're not actually fixed because they're moving along, but if you were that person sitting on B, it would appear as though it's fixed. It would also, if it's spinning this way, it would have a positive X and a positive Y component. Positive X component, positive Y component. So in fact, visually, this matches up with just what we would perceive. It matches up with the dot products. So at this point, I feel pretty comfortable that we're okay. And now I'll reset my mind and work on the other link. The other link being DC. So it's pretty obvious because here's D, and I'm not even going to finish this, but luckily I'll have a picture and I can finish this next time. Here's D, here's C. I don't know which way it's going, but I know a positive looks like that, so I'm assuming it to be positive. So it should have a negative X and a positive Y. Let's take a look at it. Cofactor expansion, 0, omega DC, a 5, nothing, minus J, and clear those out to get minus 2, omega DC, 0. Now, if you look at this, it is that minus this, minus 5 omega DC I, That minus that with a minus in front of it is 2 mega DC J. So in fact, it does have a negative I component, positive J component. Now, does the dot product of this collapse out? Well, yeah, minus 5 omega DC times 2 plus 2 omega DC times 5. Those both cancel out, you add them together. So in fact, this vector is perpendicular to dot. It's also perpendicular to dot as well. So now, I can basically erase this and grab this, minus 30I plus 30J. Look at the I component, look at the J component. Let me set these up and I should be able to solve them next time. So if I look at this, I'll see 6 mega BC. I could see minus 30, looking at only the I's. And then on the other side, I see minus 5 mega DC. So I'm looking at only the I components, be this one, that one, that one. Only the J components, I see mega BC 5, mega BC. I see this one, and I see that one that's way over there, 2 mega BC. If I want to formulate this, 2 equations and 2 unknowns into a matrix, and I'll set this up and then maybe we'll go ahead, but here's what I'll see. I'll just think about this for a minute. Omega BC, omega DC. To do this, I would move this guy on the left side, move that guy on the right side. Okay, so you know what? I'm going to have to back this up a little bit. And since I'm cramming it in, I'm going to change its color. Omega BC, omega DC. And if I take this, move it to the right-hand side, it becomes plus 30. If I take this, move it to the right-hand side, it becomes minus 30. Take this, move it back over here, it becomes plus. Move this over here, it becomes minus. So first I'm going to basically work off the BC one, which will be a 6 and a 5. And then a minus 5 became a plus 5. A plus 2, but moved over, became a minus. So if you solve this, you will get omega BC and omega DC. If you want me to, I can solve it real quick on MATLAB. K is equal to, how about just do this? Inverse of a 6, 5, and 5 minus 2. That's that, times the right-hand side of 30 and minus 30. Oop. Did I put the wrong bracket? I did. I put the wrong bracket there. So I get minus 2.43 2.43, and there may be other digits. 2.4324, and then the other one 8.9189. And I'm just going to take 5 seconds and see if that seems legit. I think these two, if it's swinging this way, this one's swinging that way. So DC should be positive. I think it's a little shorter. So this, well, maybe it's a little longer. This is about 10. This is 10. So that being, you know, a high number close to 10 seems legitimate. I think this link actually is shorter than that one. So maybe that's legitimate. This one is going to be swinging this way. which is the opposite of positive, but since its arms are way out there, that kind of makes sense as well. We'll figure this out geometrically. We still haven't found the velocity of this. We still haven't done this. So what I'm going to do, so this is where we need to pick up right here. And I'll go ahead and try my best to draw that thing in the CAD. And what I'm going to do is take a picture of the board so that when we come back in, I can project it off, put it on Twitter so that I can just show the Twitter thing and we can pick this problem back up. You can see that the first thing is these problems are not short. They take a long time. And this is just the velocity. The acceleration is even longer than this. So that's why I slow down and focus on this. Yeah, there's other terms in this book, but this is the part that is the engineering. So this is why I'll end up taking an extra 2 weeks on this because I think this is important compared to the other. The other stuff you have seen before in some sort of context. I don't know, you had physics, so I don't know that context that well. I guess I'm done, and we'll pick back up on Friday, and I'll be at my conference there. Oops, I don't think I copied it all. It didn't get it all. Ooh, it didn't get it all at all.
Who that Dana said that?